Okay.
Well, our first speaker is Jason Galtieri. Jason completed his undergrad at University of Connecticut and is now working here with Professor Klein. Jason just finished up his master's thesis, and so he'll be staying on for the PhD next fall. So thank you, Jason.
Okay, so the title of my presentation is Long-Term Benefits of Differential Power Processing in Large-Scale Solar Arrays. Okay, so the outline is I'll take you through the motivation for the research, which is dealing with mismatch in solar arrays and how differential power processing has shown improvements over conventional methods. Then we can introduce some of the sources we'd expect to see in a large-scale array and how each of these sources will affect our yearly energy output. Mismatch in solar arrays is a well-known problem. So if we have two series-connected PV elements, each element will have its own current voltage characteristics given by these two IV curves. So when we have non-uniform conditions across our PV elements, each will have a different IV curve with a different maximum power point. So because it's series connected, we can only choose a single current going through both of our elements. So in this case, if we choose I1, we'll operate PV1 at its maximum power point, but PV2 will be operating in a negative voltage region, so reverse bias. And in this case, it's dissipating power rather than producing. Conversely, if we operate at I2, then both PV elements will be forward biased, but PV1 will be operating at a reduced output. So the conventional way to deal with this is to use bypass diodes in our system. This allows us to remove underperforming PV elements from the system. So in this case, we bypass PV2 if we can get more power output out of PV1 operating at its maximum power point than both elements operating at a reduced output. So this isn't ideal because we either lose, depending on our situation, whether we're bypassing or not, we either lose the power output that PV2 could have produced, or we operate both of our elements at a reduced output. So the answer to this is differential power processing, which gives us better mismatch handling capability in between PV components. So what this does is it decouples the string current between each PV component by injecting or absorbing current at each of the terminals. And this allows each PV element to operate at its local maximum power point rather than having to choose the single string current that maximizes the power out of the entire string. And it only processes the difference in power, which gives it an advantage over existing technologies. So we want to be able to, so those are the two conventions. We either have bypass diodes or TPP, and we want to be able to compare now how this will address different types of mismatch in solar arrays. The one source of mismatch is factory binning. So just due to the manufacturing process of PV cells, it's imperfect, so we get fluctuations in current and voltage of our cells that go off the factory line. And since our panels are composed of these PV cells, we see these same variations in the end product PV panel. So the way manufacturers deal with this is they bin their panels, and the general way is to bin them based on the power output of the panel. So as the panel comes off the line, they measure the power, and then the maximum power of the panel, and then depending on that, they place it into a bin. And so the bins will have a tolerance, in which case, in all panels that fit that tolerance will fall into that bin. So you can choose a nominal value and then using these ranges. So we expect the production process of our panels to follow some sort of Gaussian distribution, in which case, and so here on this left, I'm just showing an example of an output of a factory or how we'd expect the distribution to look.
Real distribution?
No, I made that based on kind of empirical values.
Would that be the expected distribution? 7 to 9 amps?
Yeah. Well, so this is kind of the outliers, I guess, of the distribution. And then I'm showing 1 to 2 standard deviations in current.
But isn't the answer yes? I mean, given that standard deviation, that would be a Gaussian, that would be what would happen with a Gaussian distribution.
Correct. But there's no, I don't think I wasn't able to find a whole lot of actual empirical value data from. I don't think factories like to put that out. So anyway, so so you can look at a solar data or solar catalog, and you can usually buy panels from individual bins, so we can see or kind of get a look at how bins are distributed. So just looking at solar catalogs, I can see that this, for example, this Solar World Sun module, you can see that it has 3 bins corresponding to power levels of 275, 280, and 285. And I don't know if you can see it, but down here we have a plus or minus 2% power bin, or power tolerance for each bin. And likewise on the sun power, another example is the sun power E20 and 19, which is just another example. So even though solar manufacturers usually market their panels as more or less a different panel, it's really just a bin of a single process. We can model factory binning by generating this IV curve population, and then from that we can construct our bins. So this I've just modeled over a large array or large range of possible open circuit current and short circuit current values, and for each value I've created an IV curve. And then from that population I can create these subpopulations where each one corresponds to a bin. So I've chosen a nominal value which would more or less fall right in here, and then this red area corresponds to a minus 5% bin, and this green area corresponds to a plus 5% bin. So then, if I wanted to model an array, or I can construct a row by selecting panels out of one of my bins. So I've done that here for my minus 5% bin. I've constructed a row of 10 panels, and here I'm showing the power output of each panel, so we can see that each panel can vary between plus and minus 5%.
You assume they're uniformly distributed over that?
I'm assuming I'm assuming the whole population falls within some sort of distribution like that. Okay. So we expect that more of our would fall towards the average of our whole population. So I'm expecting more would fall up in this range rather than in this range, or at the bottom of the bin, if this P nominal is my average of my total distribution, of which all my bins come from.
Are you using a Gaussian distribution to generate these possible
Yes.
values?
This is just showing where how mismatch from factory binning occurs. So here I'm showing the PI curves for each of my panels down here. And so this zoomed out version isn't really helpful, but if we zoom in on the tops of our curves where the maximum power happens, we can see that each dot corresponds to the maximum power of each curve. And when we just have bypass diodes, then we have to choose a single string current for the entire string. And so this this dashed black line shows the current which maximizes the power output of our total row, but we can see that only more or less one of the curves actually correspond to that maximum power point current. So we're losing power from all the other curves because they all can't operate at their maximum power point. We want to investigate how this would actually translate to an array. We can model using solar data. So I've chosen the University of Illinois Bonneville solar data to actually model how these arrays with and without DPP would produce energy over a given year. And so since we're assuming that factory binning is a static source of mismatch, the x-axis isn't really useful here because each year we'd expect it to be more or less the same. But we can see that DPP provides about a 0.7% improvement in energy output over a row which is bypass times. And this is important because this is from the day your row is installed that you're getting this energy improvement. So this other one, so here as the years go on, we'd actually expect we'd see degradation in our panels. So here now I'm including an additional source of mismatch, which is cell degradation. So I've just randomly assigned. So this 80% bin is most manufacturers offer a 25-year warranty, which they guarantee 80% power at 25 years. So I'm using that as a guideline, and I'm randomly assigning degradation rates to each of my panels, because we know that they assume they degrade at different rates. So we can see that when we now how we have two sources of mismatch in our row, And so now with factory binning in, with cell degradation, we can see that as the years go on, we experience more mismatch between our rows, and we see that the results with DPP and without DPP begin to diverge. So we expect that rows with DPP will be able to better handle these combined sources of mismatch. We can also assume the case where now we have maybe an accelerated panel that degrades at an accelerated rate, so maybe it's an atypical value, or it's just somehow made it past a quality assurance, or it's hot-spotted. Or there's many ways that a panel can degrade faster than you would expect. So now, when we include this value, so now we're including a heavily mismatched panel in.
Oh, I had a question. The degradation rates, did you just use one randomly chosen set, or did you do like Monte Carlo simulation to see what?
So for this, I've just randomly assigned degradation rates between using this kind of as a baseline. So this kind of just like for my fusion JSON, yeah. But I've done Monte Carlo simulations, looked at that and other.
Oh.
It's not done here. Now when we have a heavily mismatched cell, or a heavily mismatched panel in our array, in addition to the other ones mismatched, we can see that when we just have bypass diodes in our row that are array without DPP performs much worse as it can't handle the mismatch. And also as it degrades, as it keeps degrading around year 19, this shift in line tells us that now that panel is bypassed, and so from here on, from year 19 on, that panel's not even producing power anymore, because the array can do better by just bypassing that heavily mismatched cell. So, although it can continue producing power just at a much lower rate, we're losing all that power here when we just have bypass diodes. Okay, so now we can add a third source of mismatch into our array and model how our row of panels would do if it was in an array of panels. So kind of working off of some of my previous presentations, here I'm incorporating self-shading and diffuse masking into the array, so at certain times of the day or year, we can have forward rows begin to shade the rearward rows in our panel. And so if the array we've been modeling this entire time is now part of an array, we could have a third source of mismatch. And I'm just assuming these values. So when we now we are incorporating three sources of mismatch into our panel, we can see that kind of the difference between panels with DPP and without the difference continues to increase. So it's kind of the point here is that as we add more and more mismatch sources that we'd expect to see, we'd see a larger and larger difference between our panels with DPP and without. Conclusion, mismatch in solar arrays arises from a variety of sources, and many of them are unavoidable. So even if we design our array to have very little shading mismatch, we'll still have cell degradation, or even if we pay a lot of money to have really stringently matched or stringently binned panels coming out of the factory, we'll still have some cell degradation and shading in our array. So we can never really avoid all the mismatch we'd expect to see in a solar array. So in that case, when we have DPP, then we show that DPP improves our energy harvest when mismatch is present. And as the number of mismatch sources increase, this improvement also increases. So, maybe just advance it. Okay. So in here, we're just assuming three sources of mismatch in an array, but there's many others that we can begin to model and add into our solar model. And these are just some of them, which I'm not going to really go through, but you can see that there's many more that we can begin to include. Okay, so I can take questions.
Did you factor in any efficiency hits due to the differential power processing?
No, so we're still assuming ideal converters here, but I should have actually included that in future work. But I think one of the problems, not problems, but DPP, once you get to a certain point where you're really heavily mismatched, at that point it might not be worth it to actually run your converters. It might be better to just bypass the panel or run your converters in some active bypass. And so we still have, I think, research still needs to be done on when that is the case. So I think if you just model that your converters are always running, and that is less one max, then that may not be the optimal. So I think at some point it's not, it may not be a good direction to run the converters.
Well, but I guess a comment on that, it seemed like the sources of mismatch you were talking about today were at the level of a few percent at the most. So again, the DPP units would only be processing a few percent of the total power.
Right.
So even if they're 90% efficient, they're losing 10% of a small fraction.
Right.
So compared to any other method one might try to use, the potential losses are really, really low, right?
Right.
It's only when you get to these sources of potentially much larger mismatch that the other mismatch kick in.
Right. So I guess if you're looking at a snapshot, a DPP operation versus bypass, that's a mismatch scenario. In this scenario, I might be doing a little bit worse, but in a global scheme with it over a long period of time, that might not actually be fine, or actually might not be that much, that dense to the system. Okay, thank you. That doesn't. No, that doesn't go there. Yes.
Our second speaker is T. Zhu.
Yep.
He completed his undergrad at
Tsinghua University.
in Beijing, and he's currently working on his PhD. Okay. Our second speaker today is T. Zhu. T completed his undergrad at Tsinghua University in Beijing, and he's currently working on his PhD here at the University of Illinois.
Hello everyone, today I'm going to talk about the tool to evaluate the economic value of inertia services for the power systems. I will consider the wind power to replace the conventional unit and fast acting storage resources to provide the virtual inertia services. And this is the agenda of my presentation today. And so there's a lot of wind power, solar power integrated into power systems. They have they have inertia, but it's very, very small. And the gas price is going down, so there is a lot of gas turbine units replacing the coal plants. So, but no matter what the resource mix is, we have to maintain the real power and demand imbalance at every second. But if there is some contingency happen in the system, we have a sequence of frequency response in the system from seconds to hours. So for a very short frequency response, we call inertial response. It's just a physical response of the system. The rotator kinetic energy is converted into electricity and energy to maintain the balance of real power. After that, the governor response come into play. But after that, when the frequency gets stable but not get back to the nominal frequency, the AGC, the automatic generation control, or the resolve deployment will be deployed by the control center of the ISO to get back the frequency to the nominal value. Sorry. Okay, so if the frequency response is not like sufficient enough to maintain the frequency above some limit, we will have some under frequency load shedding, or we will trip the generation because it's over frequency, under frequency. If we are so unlucky that there will be equipment damage when the frequency goes too much from the nominal value, or even the collapse of the power system. So here, there are more and more wind energy, the renewable energy and gas turbine unit. The power system is shifting toward a situation with less inertia. It means we have less capability to resist the frequency deviation from the nominal value. But as what I know, I talked with the people in MISO and PGM. They said there's no ancillary market providing the financial incentives to the market participant offering the inertia services.
It's not full screen.
So here, in this work, I modified the security constraint unit commitment to develop this tool to get the economic value, the dollar value of the inertia services, because the current the storage technique make the storage can respond in milliseconds, get to the maximum output or the maximum charging or discharging capacity. So I use the fast-acting energy storage as the alternative to provide the additional inertia into the grid. There is no real inertia, but they can make the system behave. There is additional inertia from the storage. So the primary challenge relies into here. This is the summary of the unit commitment simulation, the optimization problem, and the result provides the initial volume for the conditions we can run in the dynamic simulation. And the dynamic simulation have a lot of differential and algebra equations, but the unit commitment framework is a steady state constraint. They have steady state constraint. So how can we represent the dynamic simulation back into the steady state format is the challenge we will deal with in this work. So I deal with the challenge in 3 steps. The first step is very common to solve the dynamic simulation. We're discretizing the dynamic simulation model, and we're integrating the discrete time dynamic simulation model into the steady-state unit commitment model as the security constraints. And I will, because the ISOs prefer to use the linear constraint instead of nonlinear constraint, because it will save a lot of time to get the rough but appropriate solution. There is always an optimal, but it takes too much time to get optimal. So we want to get a near optimal solution. So they prefer linear form constraint. But here I'm not linearize the constraint. I represent the constraint in a linear form, but it's equivalent to the nonlinear constraint before. And so this is the overview of the simulation framework I have. This is the common unit commitment framework. And there's a connection between the dynamic and the steady state and the dynamic simulation. And here, the dynamic model is used as the security constraint I will use to limit the frequency deviation of the system if there's no conditions that happen. So here is the model I use. I ignore all the net effects, and I assume that all the generators move coherently as a single system math, and all the system load damping behave as lumped together. The left is the model I use, and the right one is the discretized the model I use. It's a very simple discretization method I use. But here, I just want to stop here. This model, the 5 equations, is enough for me to represent in in the unit commitment model, but I have to do some modification because there are some constraints, like the maximum cannot be represented in the optimization problem.
The maximum of what?
The maximum, the function here, like we have to, this is the nonlinear constraint, and it cannot directly represent in a constraint in a linear or nonlinear way. So we have to modify this constraint into a linear forms for it to be represented in a unit commitment framework. And before I talk about how I do the integration, I just want to talk about what's the unit commitment and what's the economic dispatch. What we pay for the electricity is determined from the economic dispatch. It determines how much we get from each plant, how much do we pay for that plant, the generation. But the unit commitment is used to determine the commitment plan, which minimize the electricity production cost while satisfying a lot of like physical and optimal constraints. These two may or may not have the same constraint. Just depends on what the operator likes. Here is the objective function in my unit commitment framework. I consider the generation cost, the startup cost, and the reserve cost. The reserve cost consists in three parts: the up, down, and the non-spanning reserve. And the N represents the simulation. I have a simulation subgrid I have for each day. So here the N just represent, like if I use a hourly time resolution, the N is 24 for each day. Oh, sorry, the N is the 24 for each day, and the I is the number of conventional units I have. I do not consider the generation cost for the wind farm. I do not consider the generation some cost associated with the storage operation.
So are those the offers that the units would provide to the system on?
Yes, it's all. And as for the constraint, I just consider the relation between the output and the reserve. It means like only the unit have to be online to offer the up and the spanning reserve and the electricity output. And here is the ramping constraint for the unit, and here's the real power balance I consider in the model, because I do not consider network, and it's a lossless like system, so it's just like the sum of the real power is equal to the demand we have in the system. And here's the piecewise linear cost model for the generator. I don't use the quadratic cost function for the unit. And like before anything happened, the system is in steady state, and like the frequency deviation is 0, and like all the dynamic value is determined just purely based on what we have in the state constraint. So here I integrate the dynamic model into the unit commitment as a secure constraints. And I add another term that I want to say the frequency deviation must be maintained in this range. Here is a hard constraint. I do not consider any under frequency or over frequency generation or low trip, something like that. But here the problem, and we have to pay attention, only the online units can contribute the system dynamic behavior after some disturbance happens. So after I rearrange this constraint, there will be a nonlinear term, a product of two variables, and there will be a nonlinear constraint, like maximum of something or minimum of something. So I want your equivalent transformation from the nonlinear constraint to a linear constraint. So the first one is like, if I have a constraint that z equals to xb, and x is b is the binary variable and x is a continuous variable, the two equation is equivalent to the constraint here. You can say when b is 0, z must be 0, and it satisfies this constraint. Similarly, when the b is 1, z it must be x based on this constraint, but and z equals x also satisfy the constraint, the first constraint. So the equation here and the two equations here, they are equivalent. But this is in linear form, and this equation is in nonlinear form. Another nonlinear constraint is like the maximum of x1 and x2. We have to introduce two binary variables, b1 and b2, to make it linearized. to make it in a linear form. And we can say like the B1, B2 must be 1, 0 or 0, 1, and the corresponding to the equations here can make these the three equations equivalent to the nonlinear format there. So these two equivalent transformations enough for us to use to linearize the constraint we have. The first one is that we have for the product of the frequency deviation and the unit on-off state. And the second one is like for the dynamic volume here, it has a maximum and a minimum here, so I introduced three variables to do that. Actually, you can when I was running the simulation, it's okay to not include the constraint here, but sometimes it will vary when the contingency. I mean, for example, if I consider the load increase contingency, it will make the value of the dynamic value get over the limit. So I think it's better to include this.
So how many additional constraints and decision variables do you have to add in order to make these linear substitution?
Depends on how long do we consider for the dynamic simulation. So here's like the problem. Generally, if I want to have a very precise dynamic simulation result, we want to make the time resolution as small as possible. But here, because I want just like have a constraint in a rough way, so I can make the time resolution not that close to like, for example, if I can run the simulation with like 0.1 second or 0.01 second or 0.001 second. But in my simulation, I just like, when I run the simulation using 0.05 second, the simulation is pretty much close to the dynamic simulation. I use a very, very good time resolution. So I use 5 seconds as the dynamic simulation period, and I use 0.05 second as the time resolution in the dynamic simulation. It means I have 100 substep periods for the dynamic simulation. And I test the time a little bit. If I'm not the optimization designer, so I purely use the function of my lab. If I use a nonlinear constraint compared to the solution, if I use the linear representation, the time speed will improve by 5 times at least. It means if I can solve the problem of in nonlinear format by 10 seconds, I can solve the linear optimization problem by 2 seconds. It will introduce for sure it will introduce a lot of like additional constraints and additional variables, but the linear format make the optimization much more fast to solve. So here,
one more question to you.
Yeah.
So do you have a set of those constraints for each possible contingency you would consider?
In this problem, I only consider one contingency, the sudden load increase. And the reason is like, we do not expect to find all the constraints, all the n-1 security constraints in the simulation, because it will make too complicated to solve. We can, because I haven't finished that part, I want like, if I can choose a sudden load increase with a certain amount, make that this amount, the result, the unit commit result can make the dynamic simulation all above the predefined limit. After I will finish the unit commitment, I think that deal will be very good. I don't want to have all the contingency considered in the model.
Yeah, would it be like just conventional contingency selection, or you wouldn't consider all the contingencies?
I didn't consider all the contingencies right now. What I was thinking is like, for example, if I consider the generation outage, I only need to consider the maximum, the outage of the unit with the largest like output to be outage. Then it will represent all the contingency. It can represent all the contingency. Mm-hmm. To find the economic value of the inertia, I just say, I run the simulation without any additional inertia. Then I run the simulation with additional inertia, like by a certain amount, like 0.1 second. I compare the production cost of the unit commitment. Then that's the total production cost increment approximates the economic value of the inertia services. But here, that is not the price of inertia. It just represents that if I can introduce that part of inertia, it will reduce the total protection cost. And that means that we can use that much of money to pay, maybe partial of the money, to pay the inertia services. And as I don't want to talk about we can add some inertia, but there are some way we can add some virtual inertia in the system. The product provided by the fast responding storage. So if the theta n represent the output of the storage, if I use some regular storage during the dynamic simulation, the theta n is fixed to the scheduled value. But if I have some very specified and fast responding control algorithm, I can have the system to behave that there is additional inertia to the system. But there is no inertia. Just like the system behaves, there is the inertia provided by the storage. So before I have if the frequency deviation is determined by the equation here, but I want to say the theta, the output of the storage is controlled by some algorithm, and the system behave like there is some additional inertia, and the output of the storage remain the same. Then I get the control algorithm I have. The theta n is determined by the inertia you want to add into the system, and what's the frequency, what's the change rate of the frequency deviation.
Can you back up one? Okay, so I guess I'm curious from what you just said. Presumably you could, if it's storage, you could set H to almost any value.
Yes, like for example, theta n is controllable. We want to control theta n such that the equation, the result of this equation is equivalent to the result of this equation. Here I change two terms here. The one is I add an additional inertia into the system, and I fix the output of the storage.
Okay, so in some sense your Hn prime is a function of theta.
You can have H prime n as a function of something, but you can also fix it. Like you want to say the storage must provide a 1 second inertia or 2 second inertia.
Right, I'm just trying to get a better intuitive feel for how I actually set that.
It's like if this is the output, for example, the storage output is like 0 at the beginning. So I want to control the output of the storage like this, and it's equivalent. And this is what's provided by the storage. And I want to say it's equivalent to the storage. The output of storage remains 0, but there's some additional inertia here. It's like in a mathematical way, these two are equivalent to make the system frequency behave in the same way. So I run some simulation. Could
you go back to that same slide, Professor Cried? So, like, is there a way to choose your inertia to behave in a certain way that's better than how a machine behaves?
Mm-hmm.
Is that what you've done here? Like, how did you decide to make your inertia behave that way?
What do?
So, if you can have this stored energy respond to some sort of disturbance or contingency, how do you decide how you want it to respond? In the sense that, maybe you can make it respond better than a machine can. So maybe it's not a good idea to exactly model it after a machine.
So my question is for example, if there is a contingency and you have a storage, so if you can only measure the frequency of the grid, so what's the response you want to provide? You want to have the output, storage output at the maximum or the minimal or nothing, something like that. So I just say it behaves like it just provides the inertia service by a certain amount. And okay, yeah, and just like use this control algorithm I have, it's like the frequency deviation change rate is used to determine what's the output of the storage at that time.
Okay.
So similarly, I have the steady state constraint for the storage, and the dynamics constraint for storage as well, because like it's still a maximum minimal stuff, so I have to have the equivalent representation as well. I run some simulations, like there are 10 units here there, and they have a varying like inertia, and they have the same parameter for the time constant. I suppose there is like 1 per unit sudden load increase, and I assume that the storage can provide 3 seconds, 6 seconds, 9 seconds, or 0 second inertial services. So this is the storage output during the time, and this is the frequency response during the time. So here I don't have any constraint on the capacity of the storage, but actually we don't have we cannot have a sufficient large storage. There must be some limit on the contingency. So I also run the simulation on the same contingency, but the maximum capacity is limited by 30, 20, 10, or 5 respectively. So we can see that for example 5.
What was the total capacity of the generation again?
Oh, this is the maximum charging discharging rate.
No, but for the system you're considering, what's the total capacity of the generation?
12 per unit.
And what contingency are you considering?
1 per unit, a sudden load increase. It's very large. I just want to show the curve here, how do they behave. And here we can see like as the capacity is more smaller, the performance gets worse and worse till there's no storage or there's no inertia provided storage. And I checked the IEEE website. There's only one paper talking about the inertia provided storage. It's like hardware-based stuff. They design such a storage. So here I just talk about how to apply and how to design the control algorithm for the storage. Actually, they can do that fast, 1 millisecond. So here's the test system they have, and I just use the 24-bus IEEE RTS system, and the up-down loss value reserve is set at 5%, 2%, and 5% respectively, and I also consider this as the wind turbine I have. First, I just want to show how I can determine the economic value of the inertial services. And in the second study, I want to just investigate the impacts of the wind resources and how the time varying nature, the cost of the economic value of the inertia has. The first one is like I vary load from 1,000 to 25,000. Oh, sorry, 2,500. As the load increase, the economic value of the inertia decrease, because when the load is very high, there are enough units online and there are enough inertia in the system. So we don't need to say, oh, we want to pay you to provide the inertia. But when the load is very low, when the load level is very low, the units, there is just like a few units online. So once there is a contingency happen, the system cannot maintain the frequency above some limit. So the provision of some additional inertia can make the units, like make the total production cost a little bit less. And the difference we can see it as the economic value of the additional inertia. And I also consider the case that the load is fixed, but the wind penetration is increased. It's just like we can view the load. We can view the wind output is a negative load. So as the wind penetration increase, the net load decrease, and the economic value is increasing. Here I want to show something about the wind the integration, that without the constraint, without the frequency constraint, the integration of wind brings down the energy cost, the average energy cost. But if we have the frequency constraint, the contribution of the renewable resources is not that significant, because like they bring their replacement of the conventional unit make the system have less inertia. We have to pay something else to like supplementing the inertial services in the system.
What is the red percentage?
All the percentage is out of the original price when there is no wind.
So it's compared to the blue bar directly.
Yes. Then I run the simulation over a day. We can see that the price of the economic value of inertia just become non-negative when the load is relatively low or the wind is very high. That means like when that load is like pretty low, there is need to provide inertia into the system. pretty much the work we have done, we just like find the security constraint in the unit commitment problem to find the economic value of the inertia services. And we also come up with the storage control algorithm to provide the so-called virtual inertia into the system. And what I want to do in the future is like, as what you told, I want to have a full representation of the conditions, maybe not full all the conditions I consider. I just want to pick out some representative one, which the result can make the system, or the result is stable in all the contingencies we have. And I also want to have some market simulation tool to get the price, to get the real price of inertia. Because what we have is the economic value of inertia. There must be some way to find the price. Then we can have the price representation in the market. So in the future, maybe we can get this stuff to some ISO guide to see whether it is possible to add the algorithm into the current clearing process. And some other renewable resources is also considered in the future. Because what I was doing as a master's student, I doing some concentrated solar pan. It's a plenty use of the solar energy, but it has a conventional steam generator and it has inertia. So maybe in the future we can say, oh, the wind might be not good because it don't have inertia. And the concentrated solar plant is a little bit better because it can provide the inertia and environmental friendly generation. Okay, that's what I want to cover today. Any questions?
Nice job. So I guess we got our Higgs paper, huh?
Yeah, I think so.
Yeah.
But that's the one has some more simulation without see.
But you don't want to put too much in it.
I just want to write it down on one paper, then we can put on one file.